Hi there, thanks for joining us again. This is Space Nuts, a Q&A edition. My name is Andrew Dunkley, your host. It's good to have your company. Questions today coming from Matt, who wants to talk about the oceans on Earth. Doug is asking about the stiffness of space-time. We have talked about that before, but he's got a different idea. John is asking questions about a new antenna array, and Rusty is honing in on something we talked about late last year, the largest impact crater. He wants to go further than the surface of the Earth. So we'll talk about all of that on this episode of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2.
1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And he's done all his homework. He's ready to go. It's Professor Fred Watson, astronomer at large. Hello, Fred.
I've just realised there was one bit of homework that I didn't do, which never mind. It'll be all right.
There's this thing called guessing. We can do that.
Yes.
We can do that.
Yeah.
That'll solve it. Shall we just get straight into it?
I think we ought to, yes. I think that would be a very good thing to do.
All right. Our first question is a text question from Matt. Hi, Andrew and Fred. I have a question for you. That's good because this is the Q&A segment. So it's good that you've got a question. I was thinking about what the Earth's surface would look like as a rocky planet without any water. Imagine if you happened to live by the sea and could stand on the surface, how different your part of the world would suddenly look. You'd probably fall a long way too in some parts of the world. That started me thinking, what is it that determines how far our oceans got filled up? Why, for instance, aren't they much smaller and or why aren't they much smaller and only a max of, say, a few hundred meters deep? What's the physics that governs how much total water we ended up having on Earth? And if you can share some wisdom on that, it would be grand. Thank you. I love the podcast. Been listening for a few years, but this is my first question. Keep up the good work. Thanks, Matt. Well, thanks for sending in the question. We've talked about how water ended up on Earth, and there are all sorts of, initially the thought was it's, carried by asteroids, but then they started thinking, no, it wouldn't carry enough. And the latest theory is that when the accretion of the planet happened, the water was already there, which would probably go a long way to answering Matt's question about how come there's this much.
But yes, maybe that's right. In fact, you probably answered it in that regard. Although I think the asteroid and comet theory still carries weight. And
holds water?
It holds water, yes. I was avoiding that term.
The
thing that put doubt on that was the mixture between heavy water and normal water, the isotope ratio, because that mixture in the Earth's oceans doesn't really match what we find in comets, because we can analyze the vapors that they give off when they get near the sun. And in fact, we brought samples back from certainly from asteroids. But you're right. I think the prevalent idea is that the water was intrinsic to the Earth's formation, and maybe it just got topped up a bit by asteroids and comets. So that does, to some extent, answer the question. It's to do with the inherent mix, molecular mix of the constituents of the cloud of gas and dust from which the Earth and the Sun and the solar system were formed. I think it's not necessarily a done deal, though, because we think about some of the ice moons of the solar system, which are effectively covered in water. They have far more water than the Earth has in its oceans. And I'm talking now about places like Europa, like Titan, Saturn's moon Titan, Jupiter's moon Europa. These are ice worlds. They've got a liquid water ocean with a covering of solid ice on top of that. So they're basically global water worlds, except they're covered with ice. So a bigger world of that kind could have a global ocean. And when we're talking about K2-18b, that planet whose atmosphere has shown some possible biomarker chemicals, one of the possible scenarios on K2-18b is a world that is actually covered in water, that it's a global ocean, that it's got a thick enough atmosphere that the atmospheric pressure balances out the water surface. So you've got the situation like we have on Earth, where you've got equilibrium between the liquid and the atmosphere. So it may be that, our Earth could have had more water. Maybe some of it's evaporated, maybe some of it has dissociated into its component chemicals, component elements, hydrogen and oxygen, and which have been lost into space, as we think has happened on the planet Mars. So maybe, there is certainly Snowball Earth is one of the things that we think happened in the history of our planet, that it was covered with ice, with an icy surface. It's a great question that Matt asks, though, about, what the Earth would be like if you imagined it without the oceans. There'd be those trenches. What's the deepest one? 8 kilometers or something like that?
Yes, San Andreas, I think.
Which would be pretty impressive.
Yeah. Oh, can you imagine the Earth without water?
Yes, that's right.
San Andreas. No, it's not San Andreas.
No,
it's the what's it called? Pacific Trench.
Yes, it's a Pacific one. I can't remember either. Never mind.
The Marinara Trench.
That's the one.
Yeah, it's incredibly deep. It's about...
I think it's 8 kilometers.
Yeah, I'm just trying to find it now.
Check it out, Andrew.
But if you imagine Earth without water, you could do some incredible skydiving there, I reckon, without having to catch a plane.
Yeah.
Yeah, but getting out, that would be the fun part, I imagine. But it's I can't find the depth of it, but it is something massive. But they have sent submarines down deep into it.
Yes, without people on board.
Yeah. Here it is, 26,850 feet or 8,184 meters deep.
What I said.
Yeah.
Doing all right.
You're doing very well. So, Matt, if the Earth did not have oceans, it would look very, very different. It'd be quite spectacular in places, to say the least, because there are mountain ranges under the ocean, which we can't see.
Yeah,
and you've got things like Hawaii, which is a super volcano, but you can only see the tip of it.
Yes, yeah.
So
I do wonder though. So there are significant differences. So plate tectonics is the key thing here. The ocean plates are different from the continental plates, and possibly a lot of that is the fact that they're being weighed down by the water on them. So without the water, they might bounce up a bit, and you might get a much more level playing field compared with what it's like now.
Well, you see evidence of that around New Zealand, where the Milford Sound and all the other, and Dusty Sound and all those beautiful areas are. They're still lifting after the ice age, where the glaciers compressed the ground, and you can see evidence of the rebound effect. So you're right, because the water weighs. I don't know how you'd measure it, but it's incredibly heavy. It's and putting a lot of pressure on those areas. So the Earth could look very different if all the water disappeared, and it'd probably bounce back pretty quickly.
Yes, I think so.
In the scheme of
in geological time, that's right.
Yes, absolutely. Thanks for the question, Matt. Hope we adequately answered that for you. Our next question's an audio question from Doug.
Hi, this is Doug and Hazel the Wonder Doodle calling from Whitby, Ontario, Canada. Second-time caller. Thanks very much for the show. The question today from Hazel is, we've heard people talk about the stiffness of space-time being something like 100 billion times stiffer than steel. And we're wondering how that can be when space-time isn't matter, so to speak. How can you measure the stiffness of space-time? And what exactly are you measuring? Thank you.
How long's a piece of string?
It's a great question, and I appreciate that one because this is one that has always fascinated me. So what you do is you look at the way matter distorts space, and we know that very, very well from Einstein's general theory of relativity. We know what the distortion is for a given amount of mass and a given size. It's why we understand black holes, because of the fact that the space is so highly distorted. So what you do, you look at the way matter distorts space, and from that you can determine a property called the Young's modulus of space, which is a kind of geometrical property. It's usually applied to solids, as exactly as Doug has said. How can you measure its stiffness when it's not a solid? So what you do is you know that it's flexible. You can see the way matter flexes it, and you go from there to saying if it was a solid, it would have this property. And the property we measure is something called Young's modulus. I remember doing Young's modulus as a physics experiment at school. You hang weights on a bit of wire, and that gives you the amount of stretch, the stiffness of the wire with the weights hanging on it. And so you can do an equivalent thing. And it's exactly the number, actually, that Doug has said. It's 100 billion times stiffer than steel, 10 to the power 20. There's a paper, it's pretty easy to find it on the web. It was written by, let me see if I can bring it up. It is by Kirk T. MacDonald, who's at Princeton University. So this is probably the almost the headquarters of gravity, because that's where Einstein did a lot of his work. He's got a little paper that you can find online. What is the stiffness of space-time? And the answer I've given is the classical answer, the 10 to the power 20. He's got a quantum answer as well, and you can throw in something about cosmological sound waves and electromagnetic waves and enjoy yourself with some of the equations there. But that's basically where that number comes from. It comes from that paper.
Yeah, and it's not so much about the physical attributes of the universe. It's about the fabric of space-time itself and
the way it behaves.
Yeah.
Yes,
yeah.
That's right.
Because we have talked about it before, and I think when we first talked about it, I was quite astonished by how stiff space is.
Yes.
In the scheme of things. But when you compare it to steel, I guess it puts you in a mindset of a physical thing.
Yeah, that's right.
Like an object, but that's not really what it's about.
No.
All right. Short answer, but that's pretty well documented, and you can certainly look that article up, Doug, and learn more about it. And thanks for the question, and thanks for introducing us to your puppy dog. This is Space Nuts, Andrew Dunkley with Professor Fred Watson, a Q&A edition. If you're heading overseas soon and you want to be able to get data on your mobile service or your cell phone while you're in another country, you're probably thinking, well, how can I do it? How can I get reliability? How can I get something that's not going to break the bank? The answer is Saily, S-A-I-L-Y, Saily. And, of course, they're offering a special deal for Space Nuts listeners, so don't forget the coupon code, Space Nuts, when you go to their checkout, saily.com/spacenuts. What they're offering is an exclusive discount on eSIMs. So you can save big on travel data plans. You can surf the web abroad without having to worry about a thing and without roaming fees. Now, I did use Saily on a recent trip, so I can tell you without a shadow of a doubt, it works. I did not have a problem with it anywhere we went, and it was high-quality data capture. I didn't have any lag. Didn't have any problem loading pages and maps. I didn't have any dropouts. It just worked. And that's what you want when you're overseas. And I would have no hesitation in recommending it. So how do you get the deal? Well, you go to saily.com/spacenuts and you click Get the Deal, which I'll do right now. And it will take you through all the options. You can pick a country that you're going to, from Afghanistan right through to Zimbabwe and everything in between. Or you can get a region. Now, getting a package for a region is a really great idea because you can go to several countries within that area and you're covered. And the prices vary according to which package you get and where you're going. But, you know, it is very, very inexpensive. Prices vary, of course, but there's an exclusive deal right now. You can get this at saily.com/spacenuts, and don't forget the code SpaceNuts at the checkout for a 15% discount. Grab your deal today at saily.com/spacenuts. Get an eSIM at rock bottom prices. They've cut the prices for Space Nuts listeners, and all you have to do is go online to saily.com/spacenuts and find the package that works for you from our sponsor, Saily.
Roger, you're loud and clear here also.
Space Nuts.
Our next question comes from John. I live in Cloudcroft, New Mexico in the United States. Today's Albuquerque, New Mexico newspaper reported on NGVLA. It will replace an existing 27 antenna array with 192. Each new foundation, 430 tons. Each new antenna generating 1.5 terabytes per second. And each 18-meter tall structure weighing 130 tons. How will this new antenna fit into the astronomy community? And he makes a reference to the square kilometre array and meerkat arrays that are being set up in Australia and South Africa. Thank you, John. I didn't know about this one.
Yeah, it's been in the pipeline quite a while. So the VLA is the Very Large Array. It's in New Mexico. We visited it a few years ago. A very impressive set of antennas. Essentially, it's been a really productive machine for research, the VLA, going back to the 1970s. And there's a note on their website that says it's been used for more than 11,000 different observing projects and had an impact on nearly every branch of astronomy. So what is happening now is an upgrade to make it the next generation Very Large Array, the NGVLA. And exactly as John says, it's got similarities to the mid-frequency component of the square kilometre array, which is in South Africa and is basically an extension of Meerkat, which is an existing array in South Africa. That also will have antennas about 200, much the same as the NGVLA will have. What I was looking for, and this is a bit of homework that I didn't actually do, it's going to have a frequency range, which I am not sure about. It's probably quite similar.
1.2 gigahertz or 21 centimeters to 116 gigahertz.
Okay, that's rather more, I think, than the mid frequency of the square kilometre observatory. I think, though, the other thing is that the NGVLA will have a much wider spacing of the antennas. They're talking about over nearly 9,000 kilometers. So this is continent-wide stuff. And that's certainly bigger than the array in South Africa. And so it will probably be used for different science. So the answer to John's question is that, yes, these things do dovetail together, maybe in frequency and in spacing, in antenna spacing. It's the sort of thing that astronomers, they don't tend to work in isolation. They have complementary things. And it's a bit like the 3 ELTs that are currently being planned or built, extremely large telescopes. These are optical telescopes in the 20 to 30 meter class. There's only one of them that's anywhere near completion, and that's the European Extremely Large Telescope, 39-meter instrument. But there are 2 others that are still on the stocks. I don't know how the current funding situation in the US will affect them because they require a huge component of US funding, even though they're international projects. They're the Giant Magellan Telescope and the TMT, the 30-meter telescope in Hawaii. So that it's a similar situation, I think. You've got differences. There are nuances of differences between them. They will have different strengths in terms of their capabilities, and the astronomical community throughout the world will be glad to have them, because the one thing that we're always short of is astronomical facilities. Telescopes are rare things when it comes to this, things of this size, of this stature. So great to welcome the NGVLA into the mix.
Yeah, they say the array will achieve high surface brightness sensitivity and high fidelity imaging on angular scales down to the milliarc second.
Yeah.
And it will extend out to 1,000 kilometers, and it'll have longer baselines reaching across North America and Hawaii.
Yeah.
So it's pretty impressive
long
stuff.
that comes from.
Yeah. Incredible.
I mean, we've seen this already with the Event Horizon Telescope, which goes over basically the diameter of the Earth is the baseline for that. But it's only, I think that's only 9 telescopes or something like that, or 9 observatories.
Yeah. I mean, I think it's great that they can integrate so much hardware over such vast distances to make them, super telescopes basically. And they're so much more powerful, and the data will be very interesting. I'm sure we'll be talking about it at some stage, John. So keep your ear to the podcast platform that you use, and there will be more. Thanks for the question. Let's take a little break from the show to tell you about our sponsor, Insta360. I'm going to tell you about their new camera. Just keep in mind, as a Space Nuts listener, there's a special offer for you, and we'll tell you about that in a little while. But Insta360's new camera is very exciting. It's their new flagship 360-degree camera, and it does exactly what it sounds like it does. It can take footage in 360 degrees. All you have to do is push record and it'll do the rest. And it does it in 8K. And they've also enhanced the low light performance, so you'll get outstanding images day or night. If you're a thrill seeker and you love to jump off cliffs and you want a good camera to do that, this will do it for you. If you like to go deep sea diving, you can do that with this camera. If you just want to take a great camera on holidays, it'll do that brilliantly. And it's just taking night shooting to a whole new level as well. Now, with 360-degree video capture, you can get everything around you just by hitting record, find your focus, choose the best angles later with their AI technology. They've got an AI-powered reframing tool, and you do it all through the Insta360 app. It couldn't be more simple. They have built a really tough camera, and it's got replaceable lenses. So if you bung something up, they can, just get a new lens. It'll take some work to break, though, because it's got very, very tough optical glass. They describe it as a superior drop resistance, and plenty more as well. Now, if you would like to get one of these cameras, they're offering a special deal for Space Nuts listeners. The first 30 purchases will get a free 114 centimeter invisible selfie stick worth around $25 US. That's with your Insta360 X5 standard package purchase. All you have to do is head to store.insta360.com and use the promo code SpaceNuts. Very important. Store.insta360.com and use the promo code SpaceNuts. And that deal with the invisible selfie stick available for the first 30 standard package purchases only. And if you want more information, check out our show notes. But just remember the URL, store.insta360.com and the promo code SpaceNuts. Now, back to the show.
Okay, we checked all 4 systems and keying with a go.
Space Nuts.
One final question. This one comes from, you'll never guess, Rusty in Donnybrook.
Hi, Fred and Andrew. It's Rusty in Donnybrook. Andrew, it's good to have you back, but didn't Heidi do a great job in your absence? How did you find her? Questions about the largest crater in the solar system. I presume that the one you spoke about last September on Ganymede at 1,600 kilometre diameter is larger than the one on the moon, the Aitken Basin. So the title of largest would then change to the one on Ganymede. Does it have a name yet? And I'm just wondering about Triton. Its odd shape would have to have come from an impact collision. And I'm wondering if that qualifies as a crater. It took away about a third of the moon, that impact. And was that impact with the planet, or did it acquire its odd shape by hitting something else? Thanks, guys. Cheers.
Thanks, Rusty. Always good to hear from you, chucking us curveballs. I'll answer his first question. How did we find Heidi? Heidi found us. Heidi was a Space Nuts listener, and she came to us to say, look, I've got an idea and I just want to sort of go to school off you guys to find out how I can get my idea out there. And her idea was a podcast about the relationship between real life and science fiction. And I said, well, why don't I introduce you to Hugh in the studio, if you can find him, and see what happens. And voila, Heidi's podcast became one of the Bytes.com stable, Reality Check the Science of Fiction podcast. So that's how it happened. Heidi just sort of wanted to find out how she could get her idea out there, and we took her on. Simple as that. So, it turned out to be a really great podcast series too, if you want to look it up and listen to some of the great concepts that science fiction can give to real life situations, or vice versa. Sometimes they're a little bit out there and it would never be real, but and she speaks to experts in the field about the ideas of science fiction and whether or not they're feasible in real life. It's brilliant. And yes, she did a fabulous job while I was away. So very pleased to be able to take a break and not have to have any worries at all about Fred's behaviour. Now, the largest impact crater, we did talk about that recently, and I've forgotten the nuts and bolts of Rusty's question now, but I'm sure you've done your homework, Fred.
I have. Two parts to Rusty's question. One is he talks about, and I had to go back to our podcast of the 4th of September last year to find out what we actually said. But yes, it was a story that there is evidence on Jupiter's moon Ganymede, the biggest moon in the solar system, that sometime in the past it was hit by an asteroid, probably a big one, 300 kilometers in diameter, which would have created a crater about somewhere between 1,400 and 1,600 kilometers wide on Ganymede. That's a very, very big chunk of Ganymede. Yeah. Now, that crater no longer exists. It's long gone. Ganymede has a surface that's probably icy and is being renewed all the time by probably, the activity, maybe even geysers of ice, as we see on Europa and Enceladus. So that crater isn't there anymore. And the reason why we did that story, and what has led to the idea that there was this clout of Ganymede back in the distant past, about 4 billion years ago, was what they were saying, was concentric circles, which are in the surface of Ganymede. So there's these concentric circles which are all centered on a point, which is where that impact is thought to have taken place. So there's no crater, but there are these ancient pieces of evidence of there having been an impact, these concentric circular features, which are quite prominent on Ganymede's surface. So I think the Aitken South Pole Basin still has the record for the biggest crater, certainly one of the biggest craters in the solar system. It's 2,500 kilometers in diameter. So it's actually bigger than what the Ganymede crater would have been had it still been there.
Yeah, that's amazing.
Yes, so it's a big dip in the southern polar region of the moon, and again thought to be due to an asteroid impact, perhaps in the very earliest history of the moon, 4 billion years ago or so. Now,
Well, can they glean as to how large that asteroid would have been that hit the moon?
but yes, I can't remember what the figure is. So it's a sort of almost like a planetary body. It's almost a protoplanet or something like that. So several hundred kilometers across, probably. Yeah.
Okay.
The second part of Russ's question has me very puzzled because he talks about Triton, which is the biggest moon of Neptune, and it is it's just what Rusty is saying is that it's got a big impact crater on it to make it a very odd shape. But actually, Triton's almost perfectly spherical. So I'm not quite sure what he's thinking of here, and whether he and I are at cross purposes here, whether he's thinking of another object. But Triton is a very well-behaved moon. It's in terms of its shape, it's pretty spherical. It's a large moon. It's unusual in that it orbits Neptune backwards. It's what's called a retrograde orbit. It's clockwise as seen from above the North Pole, which is backwards compared with the rest of the solar system. And so it's probably was once a dwarf planet in the Kuiper belt. So it's something that's been captured by the gravity of Neptune. But it is nicely circular, nicely spherical. So not sure about the impact crater. We might talk to Rusty again about that.
Yeah. Well, he's not. I'm not sure he'll ever send a question in again, but if he does, he can. he can follow us up and provide more clarity, I think we'll say. I just looked it up. The South Polar Aitken Basin on the Moon impact crater. You said 2,500 kilometres, so biggest in the solar system. The object, they think, was about 200 kilometres in diameter.
Okay, righto. Yeah,
that's a big hit on a small moon.
It is.
Type of situation.
Yeah.
Made a bit of a mess by the sound of it. Rusty, thank you. If you want to kind of come back to us, by all means, send us a bit more info so that we can revisit that question. And don't forget, if you've got a question for us, send us in, because we are a bit short, because I did a bit of a clean out when I got back, and we need some fresh material. So send the questions into us via our website, spacenutspodcast.com or spacenuts.io, and just that little AMA link at the top is where you can send text and audio questions, which is pretty easy if you've got a device with a microphone, whether that's a smartphone or a tablet or a computer. Send it in to us. Don't forget, as always, to tell us who you are and where you're from. We're all done, Fred. Thank you so much.
Oh, it's been a pleasure, as always, and it's always stimulating and good to chat.
It is. I love it. All right, we'll see you soon. Professor Fred Watson, astronomer at large, and thanks to Hugh in the studio, who couldn't be with us today because that's his preferred state. He just doesn't want to be with us. Thanks, Hugh. And from me, Andrew Dunkley, thanks for your company. See you on the very next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Complete Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.